It is really great and very exciting to be the first one ever to see something new. Like the first time we ever managed to capture the electron riding on a light wave, knowing that no one had ever seen it before us. It's really great. It's a totally new world that opens up. For every question we answer, we get new ones, and I find that very positive and inspiring. It means that we open new doors all the time, which brings development and research forward. We discover things that show that what we believed before is actually wrong, like the assumption that it doesn't take any time to detach an electron from an atom. Now we can measure it, and it actually takes about 20 attoseconds. It's an extremely short time, I agree, but it's not zero. To get a feeling for the timescales we're talking about, a comparison might be useful. If you compare an attosecond to a second, it's the same as 1 second relates to twice the age of the known universe. This is the timescale we need to access if we want to see how the electrons move. My research deals with light and electrons and how they interact with each other. We develop new tools that can measure motions on the attosecond timescale, the speed at which electrons move. This will give us a more accurate picture of what actually happens inside atoms and molecules. The aim is to see and capture and eventually also control the electron motion, and do that in real time. To do this, we need to tailor the light, to shape it, to look into the microcosm and hopefully see the electrons as they start to move inside and between atoms and molecules. That's what we dream about. Electrons haven't previously been studied in this way because it was not possible to generate short enough pulses and to do that in a controlled manner, and until recently nobody thought it would be even technically possible. But in 2001 two different groups succeeded in generating and also measuring the attosecond pulses, and in 2003 we did as well. If we reach our goals, our research will lead to a deeper understanding of fundamental physics, but also chemical and biological processes. All major reactions, from the effects of drugs to what's happening inside solar cell, involve electrons moving in and between atoms and molecules. By observing these movements in real time, we can understand them and hopefully also learn to control them. To make electronics faster, for instance, you have to make it smaller and smaller, and you will reach a point where you actually need to understand the intricate balance and interaction between atoms, electrons, and light. We will not cure cancer with our research. It's basic science driven by curiosity to understand the nature that surrounds us. But it will of course take us interesting and maybe also useful places. It's just like when the laser was first invented. Nobody thought it would be good for anything, but look around you today. Every time we've succeeded in measuring something new or created a new instrument, there have been new applications. Technologies being developed today are built on basic research that was developed 5 or 10 or even 100 years ago. Just like with the laser, we have a solution looking for a question, and there are a countless number of questions to be asked. It all ties together. The research, the family, the teaching. It's like when you stand with the kids at the playground, pushing them on the swings, and realizing that it's exactly the same underlying physics that govern the swing and the motion of the swing as govern the electron oscillating in a light field.